draw a free body diagram for each, or show the diagram, redraw it. Oh, or I just did a copy paste, but they're labels. I hate that stuff. So I'm going to do some slight editing here. Instead of W down, I'm going to say, hey, remember that's gravitational force, Earth on the object. Instead of N going up, that's like the normal force or the support force of, I'm going to say, like the floor on the object. And then this thrust force, yeah, I don't like that either. I'll stick with what they have there because um, it gets, I need to start doing some of the other stuff before I would have to appropriately label it. And then this D is, I think, supposed to be drag or friction, so I'm going to say friction force on the object of, I'm going to surface on the object. I guess if I'm saying floor there, I should say floor here. So kind of redrawing that free body diagram here, and then they tell us there that the sum of the forces on the object are 0. So we've got the diagram drawn, identify the direction of the acceleration vector and show it. Well, total force is 0. Remember that the sum of all forces is proportional to acceleration. That's the little proportional to symbol, Greek alpha. And so if total force is positive, then this is positive. If this is negative, this is negative. If this is 0, that's 0. So they're telling us that the total force is 0. We're telling them that the acceleration is also 0. Then write a short description of a real object for which this is a correct free body diagram. They talk about those different models or examples to use as a model. Since they're using the phrase thrust and they're looking at drag or friction forces, but they're also saying, hey, it's on a surface, my example is going to be like back in the day in your younger years in science classes, it was a pretty common thing to do what I'm going to call a balloon car, where you'd have a balloon that then has its little spout there, somehow held on there, and then this air gets squeezed out, and air gets pushed out, car gets pushed forward. If I simplify this, just focusing on the balloon and acknowledging that there's a car underneath, well, the thing that makes this balloon go forward is that inside and now this is separate. This conversation is separate from the free body diagram, from that free body diagram. So in here, the air particles, some push up, some push down. Those kind of cancel out. Some push at this angle, some push at that angle. Those cancel out. The ones that do not cancel out are the ones that end up making things interesting. So this one that pushes forward pushes the balloon forward, but the counterpart to that, those particles, those air particles, can just go straight back, and those air particles do not hit anything. So this one doesn't have a cancel force on it because the other ones can just leave. So that's actually, sometimes people will often refer to this as an example of Newton's third law stuff. It can work that way, but what we're talking about here isn't really so much a Newton's third law description. But anyway, those balloon cars are going to be my example for that.